This is going to be the third of our first series of lectures about inheritance. There's actually more to come about inheritance, but this will conclude the fundamental concepts. And indeed, the concept that's coming now is quite fundamental. It's dynamic binding, and it's the natural complement to polymorphism. In fact, it's the reason why polymorphism is useful in the first place. We change examples a bit. Not that there is anything wrong with the previous example, it's just for variety. Also, this particular example is quite common to introduce object-oriented concepts. Let's assume that we have a graphic system which enables us to display and manipulate various kinds of figures. So at the top level of this inheritance hierarchy, we have the most general notion, the notion of figure, and we have on the left some queries, on the right some commands. Center gives us the center of a figure. That's a query. Then on the right we have commands like display the figure, rotate the figure, and so on. And as you may remember, the asterisk means deferred. We haven't studied deferred classes in detail yet, but you remember that a deferred class is not completely implemented, and a deferred feature is also specified but not implemented. Then we have two kinds of figure represented here. We have open figures, like this kind of thing, which is open, and we have closed figures, which are closed. They should meet here. And closed figures have as variants the polygon, the ellipse. Of course, there's never any representation in such an inheritance graph that this is the only set of possibilities. So there's always a possibility that we add something else here. That's very important with inheritance. We never say a closed figure is either a polygon or an ellipse. We say the possibility for a closed figure is a polygon, and another possibility is an ellipse, but this doesn't preclude others being added. So a closed figure can be a polygon, it can be an ellipse. A polygon can be, among other variants, a triangle or a rectangle. And the rectangle can be a square. A square is a special case of a rectangle, in the same way that a circle is a special case of an ellipse where the two focuses are merged. On the left-hand side, examples of open figures are segments and polylines. So it's a pretty typical inheritance hierarchy. It's also a very good one for pedagogical purposes. Now, at the level of rectangle, we have features like side 1, side 2, and diagonal. These are the sides of a rectangle. Higher, at the level of polygon and closed figure, we already have a notion of perimeter. Note that for closed figure, perimeter is deferred, because we know that every closed figure will have a perimeter that can be computed, but how we compute it depends on the kind of closed figure that we have. So for that reason, we state at the level of closed figure that there is a need for a feature perimeter, and we only implement that feature in descendants, like polygon, like rectangle, or like square. So this is typical of why we use deferred classes and features. It's to capture abstractions with operations that are known to be necessary at a certain level, but not yet implemented. At the level of polygon, then perimeter is implemented. That's what the plus means, effective, in other words, implemented. And at the level of rectangle, we are going to redefine the notion of perimeter, or more precisely the implementation of perimeter, which is what the double plus means, and we're going to see these implementations in a second. Okay, so this is the overall inheritance hierarchy, and let's now look at some of the code, or at least a sketch of the code. Polygon, as we've seen, inherits from closed figure, so we write it in the code. Polygon inherit closed figure. There's a creation procedure which will enable us to create a polygon, and then there's a set of features. So we have vertex, which could also be called vertices, because it actually denotes a set of one or more, actually 0 or more vertices. And it's represented by an array of points. So this notation here, we haven't seen it yet, array of points. Bear with me, we are going to see it formally in a few lectures, but you should understand what it means. It means that the data structure vertex, which represent the set of vertices of a polygon as pictured on the right, is an array, meaning a collection of points identified each by an integer, 1, 2, 3, and so on. So that's what array of points means. We have a certain number of vertices to define a polygon, and this is going to be given by the attribute vertex count. Now, if you look down at the invariant, you notice two things, which are properties of the class polygon. One is that we only consider polygons with at least 3 vertices. Earlier on I said 0 or more, but in practice a polygon with 0, 1 or 2 vertices doesn't make much sense, so we only consider that that a figure is a polygon if it has 3 vertices or more. And the next piece of the invariant tells us of a consistency property between the array that represents the polygon and the polygon itself. The class array has a feature count which gives the number of elements in an array. So vertex.count is the size of the array. And vertex underscore count refers to the feature of the class polygon, and here we are saying, well, the representation of the polygon given by the array has to be consistent with the view of the polygon that we have in the class polygon, as given by here the feature, specifically the attribute vertex count, vertex underscore count. Okay, and now we come to the core of the example. We have the feature perimeter. What kind of feature is it in our classification of features? Perimeter is a function. Why is it a function? Well, first it's a query because it returns a result, and as a query it could be an attribute or a function. You can see that on the previous line vertex count doesn't have an implementation, so it's an attribute, but perimeter has an implementation given by this do end clause, so we know it's a function. Now the details can be filled in later on. What's really important is that when I refer to the details, I mean these little 3 dots here. When we study loops in a couple of lectures, you'll be able to fill this in. So what's a loop? It's a mechanism that makes it possible to repeat a certain operation. And we're going to study loops in the next set of lectures about control structures, but the overall scheme should be clear enough. We repeat this operation of updating the result. Result is what we are going to return as a result of calling the function, this real number. Result is a keyword, a reserved word to be more specific, and is such that the final value of result is what a call to perimeter is going to return. So each time through the loop, we update the result computed so far. Initially it will be 0. We update it by the distance from vertex number I to vertex number I plus 1. And it needs to be done a bit better than that, because when we get to the last vertex, we don't want I plus 1. Maybe we want I plus 1 modulo vertex count, because the next vertex is the first. So the details are a bit hazy here, but the general scheme is very clear. In order to compute the perimeter of a polygon, we want to go around the polygon and compute the successive distances between adjacent vertices of the polygon, which is what this expression here does. Vertex of I dot distance to a vertex of I plus 1. With a function distance, that should be applicable to points, giving us the distance from a point P to a point Q. Well, that's how we compute the perimeter of a polygon if we know nothing special about the polygon. It's just a general polygon, so there's no better way of computing its perimeter than to go around and compute the successive distances as we have seen. Now we come to rectangles. A rectangle is certainly a polygon. It's a special case of a polygon. So we say that rectangle inherits from polygon, and there's this new clause, redefined parameter, which announces at the beginning of the class that one or more, in this case just one feature of a polygon, a feature that rectangle inherits from class polygon, is going to have a new version in the new class. So this is new. So far, when a class was inheriting from another class, it was inheriting everything, all the features. Now we're still inheriting all the features, but we don't have to take them exactly as they are. We can adapt some of them to our own purposes. Why do we do this here? Well, you see it a little further below. We have a better way, a smarter way, a more efficient way of computing the perimeter if we know that instead of a general polygon, we have a rectangle. And rectangle has features diagonal, side 1 and side 2. So to compute the perimeter, it suffices to compute, as shown here, twice side 1 plus side 2. It's going to yield in principle the same result, but it's definitely faster than going around, since we just do an addition and a multiplication by 2. Now, if we didn't have this clause redefined perimeter and then the class would be invalid and the compiler would reject it, because it's not permitted to have in a class two features with the same name. This is an absolute no-no. It's a very bad thing. When you have a class, every feature should have a different name, otherwise it's very confusing anyway. And so in Eiffel, this is an absolute rule. Within a class, you can only have one feature of a given name. So if we didn't say redefined parameter, then the compiler would see two versions of a feature called that way, one coming from polygon and one defined here in class rectangle. So by announcing at the top of the class redefined parameter, you're basically telling the compiler and whoever is going to read your program that it's not a mistake and you intend to redefine or override, that's another term, the version of parameter that you have inherited from your cherished parent. And this makes everything valid. Also note, by the way, the invariant, which says vertex underscore count equals 4. Are we introducing any inconsistency here? No, we are not, since in class polygon we had vertex count at least equal to 3, and now we have it equal to 4, exactly, so this is definitely compatible with the first version. And in general, when you inherit from a class, you are going to inherit not just the features, but also the properties, the constraints, technically expressed as invariants. We're going to study this in more detail later on when we look at the connection between contracts like invariance and inheritance, but it's important already to note then that when we go down an inheritance hierarchy, the invariants can only accumulate, and of course you should not introduce any new properties that are not compatible with those of the ancestors. So what we have here is an example of redefinition, which is a very important mechanism of reuse. It tells us that inheritance is not just plain reuse, it's reuse plus adaptation. And as I mentioned in an earlier lecture already, one of the difficulties of reuse in software is that unlike in disciplines which deal with material stuff like bricks or chips, we are usually not happy enough in software with having to reuse stuff exactly as it is. Sometimes, of course, it's good enough, but sometimes we have to reuse something and adapt it at the same time. And that's exactly what redefinition gives us. We inherit from a class, we get all of its features, but if there are a few features that need to be adapted to the new context, then we can redefine them. The general semantics should still be the same. If it says perimeter, it should still compute the perimeter, but it can compute it in a different way. And we will see later on how to guarantee that the semantics remain the same. And basically the answer will be that we can keep the contracts, the pre and the post condition. We can adapt them a bit in a compatible fashion, but essentially the redefinition is going to be constrained by the pre and the post condition. With this example inheritance hierarchy in mind, we can do quite interesting things going beyond polymorphism. Let's assume that we have variables p of type polygon, r of type rectangle, and t of type triangle. X is going to be an auxiliary variable to host the perimeter results. Remember the inheritance hierarchy that we had, just the relevant part here. Rectangle inherits from polygon. Polygon has a perimeter function, also does rectangle, although a different one, redefined one. And at the level of rectangle, we introduced, among others, the feature diagonal. And so let's assume that everything has been created. P is attached to an object of type polygon and R to an object of type rectangle. So what can we do, and what is the effect, and what may we not do? Well, P dot perimeter, that is definitely possible, since P is of type polygon and polygon has a perimeter feature. R dot perimeter, it's also permitted for the same reason, except that here the version that we're going to use, of course, dynamically at the time of the call is this version, the redefined version in class rectangle. That's the reason we redefined it. Also, R dot diagonal, this is perfectly okay since rectangle has a feature diagonal. On the other hand, if we try P dot diagonal, then of course that is going to be invalid and indeed rejected by the compiler, because at the level of class polygon, there is no such thing as a diagonal feature, since polygons in general do not have a diagonal. Only some kinds of polygon do. Now, as we saw in the last sub-lecture, we can also have a polymorphic assignment in which R becomes assigned to P, so the object that R was attached to will also become attached to P. And so we have this polymorphism example, the same thing as we had with trams and transports in the last lecture. That is, the possibility for a variable of type polygon to become attached to an object whose type is a descendant of polygon. Now, as we've also seen, it would not be possible to have an assignment the other way around, because even though a rectangle conforms to polygon, polygon does not conform to rectangle. In fact, it's a general rule that conformance is an anti-symmetric property, meaning that if a type conforms to another, it's only possible for that other type also to conform to the first if they are identical. It is also not permitted to have P dot diagonal even just after this polymorphic assignment P receives R. So you might be shocked at first at seeing this, but then I'm sure you will understand the reason. Of course, if we have executed P receives R and immediately afterwards we try P dot diagonal, it would work. It would work because in this particular case, the P variable is attached to a rectangle object which has a diagonal feature. But in a way, this is only by accident, it's only by chance, and we cannot know this statically. Remember, as we saw last time, that the interesting cases of polymorphism are those in which we have conditional polymorphism. Sometimes P is going to be a rectangle and sometimes it's going to be a triangle. And so a polymorphic assignment like this one is only going to happen in some cases, and we cannot be guaranteed that P dot diagonal will always be meaningful. And remember also that static typing is a guarantee on the part of the compiler. You know, you may think that static typing is a nuisance for you because sometimes you write something that you think makes sense, and the really mean compiler is going to reject it and tell you to change your program. Well, in some ways it is. But more importantly, static typing helps you because of this guarantee that I was describing. It's not just that the compiler is going to be rejecting some of your programs. It's also that if it accepts your program, then you have the guarantee that certain types of errors, certain kinds of errors are not going to happen at runtime. And these are type errors like trying to apply the feature diagonal to something that happens to be a rectangle and which doesn't have a diagonal, of course. So this is the way to look at it, and the guarantee of static typing is that x.f will always be meaningful in the sense that the object attached to x, if any, is going to have a feature for f. The next question is going to lead us to a fundamental mechanism of programming dynamic binding. The question is, what is the effect of p dot parameter in case p is a polymorphic variable? So there's no question of static typing here, because parameter, as you remember, is a feature of class polygon, although it has different implementations in different descendants. So it has a first implementation in polygon, it has a second implementation in rectangle, and although I didn't reproduce it here, in class square, there's one more implementation which is going to be simply 4 times the side, since in a square, side 1 is equal to side 2, there's only one square value. So everything is correct, valid in terms of types. That's not the question. Now we go from a static question to a dynamic question. What is the effect, dynamic question, semantic question, of p dot parameter, assuming p is polymorphic? In this example, p is sometimes attached to a rectangle object, sometimes attached to a triangle object, for which the version of parameter is the same one as inherited from polygon, the default one. And it's more interesting, as already pointed out, to consider this kind of polymorphism situation in cases like this, where we don't know ahead of time what's going to happen. So some tests could be the result of finding out where the user has clicked the mouse. Sometimes he clicks on a rectangle icon, sometimes on a triangle icon. And some test is going to be true or false depending on whether he's clicked on a rectangle icon or not. This is just an example, but it's to emphasize that we cannot know statically. It's only in one particular execution that P will become polymorphically attached to either a rectangle or a triangle object. So let's assume that in one particular execution, it was indeed assigned R. So we have two versions that we could use. We have the polygon version coming from the static type and the rectangle version coming from the dynamic type. Well, dynamic binding, which is really the correct policy, I think I can be quite strong here, it says that it doesn't matter how you declared P. What matters is the runtime form of the associated object, that is to say the dynamic type of P. And there's lots of justification for this. We declare P as a polygon in order to keep our generality, in order to keep our options open, so that in some cases it might be a triangle rather than a rectangle, or maybe something else, a square or some other kind of polygon. But in this particular case, it is a rectangle, although we only know this at runtime, and we've taken the trouble, or whoever wrote the code has taken the trouble, to provide a special version of parameter for rectangle. So it might be actually a mistake to use the inherited version. In this particular case, it would only have a performance effect because the basic parameter version is slower than the rectangle version, but in another case it could be just incorrect. The inherited version might just be wrong, and we'll see this in connection with contracts. So the policy of dynamic binding requires that the effect of a call whose target is polymorphic is deduced from the dynamic type of the object. Static binding, which is applied strangely enough in some programming languages, would be to say that the version to be applied is always the version from the static type, in this case polygon. An example of a language which has static binding by default is C++, although you can have dynamic binding by specifying a function as virtual, a C++ keyword. And in IFL or in Java, the default policy, in fact the only policy, is dynamic binding because it's the semantically correct one. We may define dynamic binding as the following property: any execution of a feature call will use the version of the feature best adapted to the type of the target object. So it might be the version redefined in the class itself, as in the case of parameter for rectangle or for square, or it could be an inherited version, but it's the closest inherited version, the one from the closest ancestor. It's also important, although I hope it's clear from the preceding discussions, not to confuse binding and typing. In both cases, binding and typing, we can have a static and a dynamic solution, and the best combination is static typing and dynamic binding. They go very well together because for a call x.f, you know the fundamental mechanism of object-oriented programming, then static typing gives us the guarantee that there is at least one version of f. We don't want to be caught at runtime with our pens down, so to speak, trying to execute f on an object which does not have such an operation. And dynamic binding, taking static typing, of course, for granted, is that once we know that we have at least one version, well, if we have more than one, we want a guarantee that for every call, we will use the most appropriate version of f, and of course, for different calls, it might be a different version. Sometimes we might have a triangle, sometimes we might have a rectangle, and the result will be different, although at a certain level of abstraction, it will not be distinguishable. It's important to understand that dynamic binding is not just a neat trick to enable us to code things a bit more efficiently. It's really a fundamental software architecture technique because it makes it possible to simplify our code dramatically, and in particular, it makes it possible to limit the amount of knowledge that various modules of a system must have. Now, one of the basic goals in software architecture is to make sure that knowledge doesn't have to spread throughout the software. Why is that? Well, things change. So, for example, if you have a list of possible figures in your system, a figure is going to be either a circle or an ellipse or a polygon or a rectangle and so on, in a fixed list. Well, what happens in software, as in the world in general, is that such lists have an unpleasant tendency to change. There will be new variants added, variants removed, and by limiting knowledge about such lists of variants to a small part of the software, possibly ideally to just one class in the entire software, we make sure that when things change, only one place has to be updated. The reverse of that is the source of many of the ills of software development, many of the difficulties of software construction. That is to say, every time there is a change, you need to update lots and lots of places throughout your software, and it's an endless task. So without dynamic binding, assume that we have, for example, the feature display, a procedure, which displays a figure. Well, we have to display a figure differently depending on exactly what kind of figure it is. So if it's a circle, then we do something else. If it is a polygon, then we do something else. If it is a triangle, we do something, and so on. That is heavy because we need to test case by case. And the worst is that we don't just do this for display, but we must do it for every routine that manipulates different kinds of figures. They're all going to have this multi-branch, case 1, case 2, and so on structure, and any change is going to ripple through the software. It's very tedious. With the techniques that we have now studied, inheritance with redefinition, polymorphism, and dynamic binding, we have a much more elegant and scalable solution. We are going to have some variables representing the different possibilities, like f of type figure, c of type circle, p of type polygon, and of course I'm only taking 2 variants of figures, but this scales up to any number. At some point we need to create objects of the appropriate types, a circle and a polygon here. And then at some point we need to have some way of initializing f, which is going to be the polymorphic variable representing all possible cases. So it's going to become, to receive the value of either C or P. It's going to become either a circle or a polygon reference. And that's it, because after that, we never again have to ask, do I have a circle? Do I have a polygon? Do I have a triangle? All that we do is rely on the beauty of dynamic binding to say, move that figure, rotate that figure, display that figure, give me the center of that figure, and so on. For any figure operation, we just apply it to f and rely on dynamic binding to make sure that whatever f actually is attached to at that particular point in time, the appropriate version of the operation is selected. So it's a fundamental software architecture technique that enables us to concentrate knowledge about the set of variants of a certain notion in just one place. One of the general problems of software construction, one of the most difficult problems, is to limit the distribution of knowledge. And the reason for this is that knowledge changes. So if you have a list of possible variants, like here, a list of types of figures, well, at a particular point in time in the evolution of the project, you will know what it is, but software is like the world at large, it changes. So new variants will be added, maybe some existing variants will be removed. And if you have the kind of structure that we had with the previous solution, there's going to be dozens of places in your system that know about the list of variants. And that's really bad, because every time there is a change, you need to trace all these places and to update all of them. So what we have with polymorphism in dynamic binding is the ability to concentrate that kind of knowledge in just one place, which is the one that we had here. It could be something else. Actually, there are even more elegant ways to do it than this multi-branch if-then-else. But the basic idea is that there should be just one place, and this is actually quite a general principle of software design, which is the single choice principle. It says that if a system supports several variants of a notion, then the knowledge about the set of variants should be limited to one module. It's not always possible to achieve this 100%, but dynamic binding goes a long way into helping you to achieve it by making sure that we make a selection between variants in one place, which is the point of single choice, and after that we rely on dynamic binding to choose between the applicable operations. So that's all for inheritance. So far, we're not finished with inheritance. We have a few more things to say, but that will be for later lectures. We have to see multiple inheritance. So far, we've concentrated on single inheritance. And there are a couple of topics of which we have had a preview, but which need to be explored further. In particular, the relationship with contracts. We've seen the rule about accumulating invariance in inheritance hierarchies, but there's more to say. And there's also going to be a bit more to say about deferred classes and features. So we have more lectures coming about inheritance later on, but for the moment we have the basics. We have seen inheritance as a type and module mechanism. As a type mechanism, it lets us organize our data abstractions into taxonomies. As a module mechanism, it's a form of reuse, which enables us to build new classes as extensions of existing ones, but also as adaptations. It's not just reducing something as it is, which is what we do with the client relation, but reusing and adapting it. In fact, I mentioned the client relation. The way we build our object-oriented software architectures is very simple. There are only two possible relations between classes, client and inheritance. Client enables us to reuse a class through its interface. Inheritance enables us to reuse it and to adapt it independently of the interface. We have seen polymorphism, which gives us flexibility, but together with type safety, and we have seen the notion of static typing. We have seen how this static typing concept can be reconciled with dynamic binding, and we've seen one more important principle of software design, which is the single choice principle.